Hi, Physics. Mr. Janowski here. This is the fourth part of the chapter 6 and 7 slides. So let's start with the do now questions. First question. When two solid objects come into contact with each other, the friction is due to surface irregularities. So even if the surfaces look very smooth, if you zoomed way in, you will see that they're irregular. They're rough. They're not perfectly smooth. They're bumpy. So the bumps are going to bump against each other. Question 2. What are the two types of friction we discussed? That would be kinetic friction and static friction. Kinetic friction is when the surfaces are actually moving. Static friction is when it's the friction that's holding them together and not allowing them to move. And of the two types, almost all of our problems will deal with kinetic friction. So what is the equation for each type? On the left, F sub k, the force of kinetic friction, is equal to mu sub k, the coefficient of kinetic friction, times the normal force. And on the right, you have your formula for static friction. But again, we're not really going to use that one. We'll talk about static friction, but we don't really use it that much. And then the fourth question, what is the equation for weight? Well, the symbol for weight is F sub g, and the formula for weight is F sub g is equal to mg. So on this slide, we talked about these four different quantities, their symbols, their units, and whether they were scalars or vectors. So I'm just going to reveal them all right here. I guess I'll do it one at a time. All right, so force due to gravity. Its symbol is F sub g. Its unit is Newton, because it's a force, and it is a vector, because it is a force, and forces are vectors. The second thing is the acceleration due to gravity. So we call it little g. Some physics textbooks actually do call it a sub g, little a sub little g. But we just call it g because we use it so often. Just call it a g. Its unit is meters per second squared because it's acceleration, and it is also a vector. So if you're comparing these two, I'm pointing these out because it is a very common mistake that people make when they're learning how to do these problems, is they confuse these ideas. So they'll get to a point where they will get to a point where they need F sub g, the force due to gravity, and instead of using its formula, which is F sub g is equal to mg, they will replace F sub g with just little g, or perhaps just with little m. So try to avoid that. When you have to replace F sub g, you want to sub in F sub g is equal to mg. The next thing, the force due to kinetic friction. That is F sub k, force of kinetic friction. It's got units of newtons because it's a force and it's a vector. And the last thing, coefficient of kinetic friction. That is mu sub k. It has no units, which is a little bit weird. It's the first quantity we've had this year that has no units. And it is a scalar. So these third and fourth things, F sub k and mu sub k, these are another pair of things that people get confused. They'll be doing the problem. They'll do their step 3. They'll list their forces. One of them will be force of kinetic friction. And then later on in step 4, where they have to sub in for F sub k, they'll just throw in the number for mu sub k. And F sub k, the force of kinetic friction, is not the same thing as mu sub k, the coefficient of kinetic friction. Remember the formula from the previous page is F sub k is equal to mu sub k times F sub n. So these are areas, subbing in for F sub g and subbing in for F sub k, where I've seen lots of students in the past make mistakes. So I'm highlighting this. Try not to make those mistakes. Then we started to deal with two-dimensional force problems with a twist, and the twist in this case is that forces will be on angles. So the question is it easier to push or pull a sled? Well, we started with the pull a sled question. So here we have Alice. She's going to pull Billy on a sled with a force of 115 newtons at an angle of 30 degrees above the horizontal. If the combined mass of Billy and the sled is 80 kilograms, and mu sub k, the coefficient of kinetic friction, is 0.10, what is the normal force on the sled, and how fast will the sled accelerate? So the things we're looking for are what are the normal force on the sled? F sub n is equal to question mark Newton. This would be our step, huh? And how fast will the sled accelerate, or how much will the sled accelerate would be a better way to say it. So that would be A is equal to question mark meters per second squared. What's the acceleration in meters per second squared? So yeah, step 1, you make your sketch, which on the homework, I've actually kind of drawn it for you. So those are our ideas. Then you make a free body diagram. So in the free body diagram, you list all of your forces. So of course we have the force of gravity going down. You have a normal force going up. because the sled in this picture is touching the ice. So that means, or touching the ground, that means the ground is pushing up on the sled. So you have the normal force. They'll be moving to the right, which means there will be a force of kinetic friction to the left. And then the final force is the force of Alice. So the force of Alice, unfortunately, is not going in a pretty direction for us. It's going at an angle. It's doing two things at once. It's going to the right and it's going up. So how do we deal with this? We deal with this the same way we dealt with ugly vectors back in the 2D kinematics chapter. Take your ugly vector, which was this purple one, do a step 0 to it, which is find its components. So this thing is going to the right and it's going up. So you want to find out how much is it going to the right, and you want to find out how much is it going up. So you do that, you get your components. It ends up being 99.6 newtons to the right and 57.5 newtons going up. So there. Let's see. What am I doing here? Looking too fast. All right. What you do now at this point is you draw a new step 2. You do a new free body diagram, only you're going to draw one that only has the pretty vectors. So f sub g, that's already okay. F sub n, that was fine. F sub k, those were fine. As far as f sub a goes, when you draw your new free body diagram, instead of drawing this ugly vector up at an angle, up and to the right at an angle, you're going to replace it with this guy, f sub ax going to the right and f sub ay going up. Just like that. So now we have a free body diagram where all of our vectors are pretty, and this is good, so we can work with this. So from here, you have to do Newton's second law, F equals ma. You're going to have to do it twice, once for the x direction, once for the y direction. And which one should you do first? You actually do the y direction first. You do the y direction first because eventually we need to know f sub k, and f sub k involves f sub n, and the only way we can figure out f sub n is by doing the y direction first. So you do the y direction. So in doing that, write sigma f sub y with a hat is equal to ma sub y with a hat. Then you go and you grab all of your y direction forces. Ignore the x direction ones. Ignore the blue ones for now. Just grab these red ones. Put hats on them and plus them all together. Remember, in step 3, all of your forces wear hats and all of your forces are plussed together. So you do that, and then you take off the hats. So here in the slides that I had prepared, I did it slightly differently in class. Well, let me start off with the left side. You take off the hats. F sub n, that's going up, so that gets a plus. F sub ay is going up, so that gets a plus. F sub g, that's going down, so that gets a minus. Now, as far as the right side goes, ma sub y with a hat. Remember, our sled is not accelerating in the y direction. That would be the sled shooting up in the air or, falling off of a cliff or something. Our sled is not going up or down at all. It's only going sideways. So that means a sub y is 0, which means the whole right side is 0. So from here, what do? We're trying to solve for f sub n. So you bring these guys over to the other side. For f sub g, you sub in mg. Again, remember the thing from the do now. Don't sub in just g or just m. F sub g is equal to mg. So you sub that in. You throw in your numbers. You do the calculation. You end up with an answer. F sub n is equal to 726.5 newtons, which is the right thing in the right units, and it's a very reasonable number for that, so we're happy about that. Then you go on and you do step 3 on the x side. So sigma f sub x is equal to ma sub x with a hat. On the left side, grab all of your x direction forces. Ignore the y ones, just grab the x ones. Put hats on them, plus them together. And this equals, on the right side, ma sub x with a hat. Step 4 is the math. You take off the hats. You put in the signs. F sub k is going left, so that gets a minus. F sub ax, that's going to the right, so that gets a plus. Gets you to here. Remember, F sub k, the force of kinetic friction, is actually mu sub k times F sub n. So you replace that guy with this. Then you divide both sides by m because we're trying to get a sub x by itself. You plug in all of your numbers, and you get an answer for a sub x. So it's an acceleration in meters per second squared. That's what we were looking for. And it's a fairly small number, which makes sense because it's, one kid pulling another kid on the sled. So they're not going to accelerate super quickly. So we were expecting a small number for this. So that was problem 1. Problem 2 was very similar, only instead of Alice pulling up and to the right, Alice will be pushing down and to the right. So she's not like pulling on a string from in front of Billy. Now she's standing behind Billy and pushing on his shoulders. So very similar problem. All the numbers are the same. The only difference is the angle. Instead of being up and to the right, is now down and to the right. And that's going to affect how you do this problem when you get to your step 2, and then your step 0, and then your next step 2. So anyhow, yeah, that's the end of the slides for this part. And hopefully you found that helpful.